So for number 1, we're trying to find the union and intersection of each of the following families or indexed collections. So for item A, first we want to do the union. So the union of A, now this A just means any of the sets in the family, right? So the union of the sets in the family, and the union, we basically find it by putting all the items that show up, or all the elements that show up in at least one of the sets. So we can see here we have from 1 through 5, and then we have 6, and then 7, and then 8. So those are all the elements. So 1, 2, 3, 4, 5, 6, 7, 8. And for the intersection of the sets and the family, we're going to have all the elements that are in all of the sets, right? So the element that shows up in all of the sets is going to be 4, because it's here and there, and we're going to have 5. So 5. Those are the only 2 elements that show up in every single set, so that's going to be 4 and 5. Now let's do B. So the union, let me write this. So the union of the sets belonging to the family, so we're basically going to join all the elements. So let's see, we have 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12, 13. So we basically have 1, 2, 3, so on until 12 and 13. And for the intersection, we can see here that there are no elements that are in every single set, right? There's nothing that they all have in common, so that is just going to be the empty set. What about C? So for item C, we have now an indexed collection where the family is going to be A1, A2, A3, A4, and so on, where the index are the natural numbers. And for each an, it begins at 5 times n, and then ends at 6 times n. So let's just list out a couple of terms here. So we have a1, so remember a1 begins at 5 times n, and it ends at 6 times n, so it'll end at 6 times 1, so 6. A2 begins at 5 times 2, so it begins at 10, and it's going to end at 6 times 2, so it's going to end at 12, and in the middle we're going to have 5 times 2, 10 plus 1, 11, so 10, 11, 12, and you guys can kind of see the pattern where A3, we're going to begin at 5 times 3, so we're going to begin at 15, and then we're going to end at 6 times 3, so we're going to end at 18, so we have 15, 16, 17, 18. For A4, we are going to begin at 5 times 4, and we're going to end at 6 times 4. So we begin at 20, and we end at 24. And you can see that with each one, the number of terms is increasing, right? So A5, we're going to begin at 5 times 5, which is 25, and end at 6 times 5, which is 30. So for A5, we have, let's see, 25, 26, 27, 28, 29, 30, and we're just going to do a couple more just so that you guys see the pattern. A6 begins at 5 times 6, which is 30, and ends at 6 times 6, which is 36. So we're going to have, let's see, begins at 30, and then it goes on until 36. And then A7, we're going to begin at 5 times 7, which is 35, and end at 6 times 7, which is 42. So we're going to have begin at 35, and then go all the way out to 42. And last one, A8, we're going to begin at 5 times 8, which is 40, and we're going to end at 6 times 8, which is 48. So we're going to end at 40, begin at 40, sorry, and then go all the way out to 48. So let's take a moment to analyze what is happening here. We can see that basically after we reach A5, that every single term is covered because we end at 30 and we begin at 30. We end at 36 and we begin at 35, right? So we back step 1. We end at 42 and we begin at 40, so we back step 2. We end at 48 and we're going to back step 3 in the next one, so we should begin at 45 and so on. So basically we can see here that every single term from 20 is covered from 20 onwards, because we go 20, 21, ends at 24, and then 25, and so on. So we're going to say here that the union of the sets in our family is going to be, so let's collect it all. So in the beginning, we're going to have 5, 6, so 5, 6, 10, 11, 12, because these don't really have overlap between them, 15, 16, 17, and 18. So these have no overlap, and then union the set of n where n is greater than or equal to 20. So we're saying that, hey, after 20, we are basically going to have every single one of them, right? Every single natural number, because for every A9, it intersects with all the previous ones, A10 intersects with the previous ones too, and so on and so forth. And so that's the union. And then the intersection, oops, I put this wrong. So the intersection is going to be of A of our family is whatever they have in common, and that's just going to be the set of n where n is greater than 20. So actually no, that is not true. The intersection is going to be empty. So I'm glad that I caught myself. So the intersection of A is going to be empty, right? Because they don't all have stuff in common. For example, the set here that has 5, 6, it has nothing else. It doesn't have the 20, 21, 22, and so on. So the intersection is just the empty set. They have nothing in common. And that's it for item. So for item D, we have here an index collection of sets. And so our family is going to be the family B, where we're going to have B1, B2, B3, and so on, indexed by the natural numbers. So let's just expand some of these out so that we get a notion of what this looks like. So basically B1 is going to be the natural numbers minus the index. So we're going to begin at 2, 3, 4, and so on, right? B2, instead of beginning at 2, it excludes 1 and 2. So we're going to begin at 3, 4, 5. B3 is going to excludes 1, 2, and 3, so it's going to begin at 4, 5, 6. B4, it excludes 1 through 4, so it begins at 5, 6, 7, and so on, right? So what is the union here? The union of the sets B belonging to the family. Well, the union is, we can see that as the index gets bigger, the set gets smaller because we keep removing elements from it, right? So the union is basically just going to be the first one. Whatever is contained, all the possible elements that are in this in the union are contained in the first one, because after that it's basically the first one, but it gets smaller. So it's going to be, we can say that this is the set of natural numbers minus the set containing 1. And now what about the intersection of B over B? Well, as you can see that it basically gets smaller and smaller. That means that they're not going to have one element that is common in every single one of them. Because suppose you have the element 1,000,000. Well, eventually you're going to get to B sub 1,000,000 where it's going to exclude that 1,000,000. So depending on the number, you can always have an index that is going to exclude that number, so which means that the intersection is going to be empty. So that's it for item D. Now let's do item E. E says let A be the set of all sets of integers that contain 10. So A is the set of all integers, the set of all sets of integers that contain 10. So A is going to be just the set containing 10 itself. Maybe we're going to have the set containing 10, 11, 12, and so on. It contains the set of integers as well, because the set of integers do include 10, right? it includes the set of positive integers, which includes 10. Maybe it includes the set containing, let's see, I don't know, 10 and -1. You can see that these are infinite, right? So the union of all of these, so union of A belonging to A, well, what is the biggest set here that contains every single element that is in this set of sets? And we can see that this is the set of integers, right? Every single possible element that is in this family is contained in the set of integers, since the family is the set of all sets of integers. What about the intersection? Well, the intersection, what is the one thing that they all have in common? It's the set containing just the element 10, right? Like that is the smallest set that could be contained in this family. And that is it for item E. Now let's do item F. So for item F, we have that A1 is 1, A2 is 2, 3, A3 is 3, 4, 5, A10 is 10, 11, all the way up through 19. And so for each AN, where the index goes from 1 to 10. So you're not going to have, for example, A11 doesn't exist, right? Because the index is constrained from going from 1 to 10. So let's do the union here. Well, the union of, let's see, A belonging to A, the union, we're going to have 1, 2, 3, 3, 4, 5. We can see that all of these sets here overlap, right? And it's going to end at 19, because 19 is the greatest one. So it goes 1, 2, and so on, 18 to 19. So that is the union. What about the intersection? Well, we can see here right in the beginning that they have nothing in common, right? A1 and A2 have nothing in common, so there isn't any value that is common in every single set in the family. So we're going to say that this here is the empty set. Okay, now let's do item G. So item G, for each natural number, so the index is going to be the natural number. We're going to have A1, A2, A3, A4, and so on. So let me just expand this. So A1 is going to be, all of them begin at 0 excluded, and it goes 1 over 1. A2 is going to begin at 0, and then it's going to go 1 over 2. A3 is going to be 0, 1 over 3, and so on and so forth. So the union of A belonging to the family, the union is going to be the biggest set, right? That since these are nested sets. And basically the biggest set is the first one because we can see that they all have the same beginning. However, let me just put A4 here as well. 0, 1/4. The left limit stays fixed, but the right-hand side, it keeps shrinking. It keeps getting smaller and smaller and smaller. So the biggest interval here is the interval from 0 to 1 excluded. And what about the intersection here? Well, the intersection, 0 is not included. So the left-hand side begins at 0, but it does not include 0. And the right-hand side, the limit of the right-hand side gets smaller and smaller and smaller. So at the limit, it's basically going to have 0 on the left and then 0 on the right. But it does not include 0, right? So 0 is not included, which means that there's no value that is common to all of these subsets. So that's just the empty set. Now let's do H. So for item H, our index is going to go from 0 to infinity, and each set in the family begins at -pi included and goes all the way out to r. So maybe you can draw this in the number line. So this is 0, and maybe that's going to be -pi. So in the number line, it's going to include here, and basically the index begins at 0 excluded, and then it goes all the way out to positive infinity. So this boundary here is going to move, right? So maybe A10, sorry, or maybe I'll put like A3. So A3 is going to be out here. Maybe I'll draw this in orange. A3 is going to be out here where this is 3. A5 is going to be out here where this is 5. So this left-hand boundary is fixed at negative pi, but the right-hand boundary begins at 0 excluded and then extends out to infinity. So once we've seen what this looks like, the union of A belonging to A, if we join all of these together, well, all of them are going to begin at negative pi included, and it's going to go out to positive infinity, right? Because it can take all those values between negative pi to positive infinity, and the intersection of A belonging to A, every single one of them is going to have this interval here in common, right? Because basically the right-hand boundary extends. So if we're at A3, it's going to have all this stuff here. If we're at maybe A5, it's going to begin here and go all the way out through there. But either way, all of them are going to have this chunk here in common. So we can say that the intersection begins at negative pi included and ends at 0 excluded. So that's it for item H. Now we want to do item I. So item I, okay, for item I, each AR, so each member of the family, is going to begin at the absolute value of R and end at 2 times the absolute value of R plus 1, where the family includes each AR for R belonging to the reals. So let's put this on a number line, and I'm going to do here -1, 0, 1, 2, 3, 4, 5, 6. Okay. So the first important thing to notice here is that this will never be negative, right? Because what if I do say A of -1? Well, A of -1 is going to begin at the absolute value of -1, and then it's going to end at 2 times the absolute value of -1 plus 1. So, which is going to be, begins at 1 and ends at 2 times 1 plus 1, 3. Right? So A of -1, it goes from 1 to 3. What if I do A of -2? Well, similarly, it's going to begin at the absolute value of -2, which is 2, and then it's going to end at 2 times the absolute value of -2, which is 4 plus 1, which is 5. So it's going to go from 2 to 5. And this absolute value here basically means that none of the boundaries can ever be 0, so it's going to begin at, say, A0, where it begins at the absolute value of 0 and ends at 2 times 0 plus 1, ends here. So let me do that in a different color. So this begins here at 0 and then ends at 1. So we can see here that these intervals, they keep shifting around to the right and they keep getting bigger, right? Like this thing here is 1. This length here is 2. This length here is 3. We can also take fractions, but the idea here is as R gets more positive, the length of the interval gets bigger and bigger and bigger, and it keeps moving on. So from this, we're ready to state the union. So the union of A belonging to A, well, it's going to begin at 0 included, right? And then it's going to go all the way out to infinity, because if you go 2 times R plus 1, you can get as infinitely big as you like. So the union goes from 0 included all the way out to infinity, and the intersection here, already from the examples that we did, we can see that the intersection is empty, right? Like, if you look at this interval here that begins at 2 and ends at 5, it has nothing in common with this interval that begins at 0 and at 1. So they don't all intersect at any value, right? So it's just going to be the empty set. That's it for item I. Now let's do item J. So for item J, we're saying for each natural number, and this is an indexed collection where we have M1, M2, M3, and so on. So for each natural number, we're basically taking that natural number and we're multiplying by the integers. So if for M1, we're basically going to have minus 3 times 1, minus 2 times 1, minus 1, 0. So we can see here, we're going to just have all the integers, right? We're going to have minus 3 times 1, which is minus 3, minus 2, minus 1, 0, 1, 2, and so on. So this has all the integers. What if we do m2? Well, we're going to take all the integers and we're going to multiply them by 2. So that's going to be, let's see, minus 6, minus 4, minus 2, 0, 2, 4, and so on. What if we do m3? m3, we're going to multiply the integers by 3. So we're going to have, let's see, it's going to be minus 9, minus 6, minus 3, 0, 3, 6, and so on and so forth. So from this, we can already see the pattern, the union. So all the values that it could possibly have, and that's going to be of m belonging to m. And that's just going to be the integers, right? It's going to be, the union's going to be the first one, where it takes on every single possible value that all these sets are going to have. So the union is just going to be the set of integers. And then what about the intersection? Well, we can see here that basically the one thing that they all have in common is the value 0, right? That's the only thing that they are all guaranteed to have in common. The rest, it's pretty much not guaranteed, right? Because say if you have 3, 3 is not going to show up everywhere. 1 is not going to show up everywhere. 2 is not going to show up everywhere, right? Like 2 does not show up in the set. So the only value that's guaranteed to show up everywhere is the value 0. So the intersection is just a set that contains 0. And that is it. I should have labeled this. That's item J. All right, so for item K, we have an indexed family of sets, but the index begins at n is equal to 3. So, and each set is going to have this rule here. So let's put a few examples so we can see the pattern. So A3 is going to begin at 1 over 3, and then the boundary is 2 plus 1/3, so that's going to be 7/3. And then A4, it begins at 1/4, and then ends at 2 plus 1/4, so that's 9 over 4. A5 begins at 1/5, and ends at 11 over 5. And I'm just gonna put the decimals here so that you guys can see the pattern as well. That's gonna be 2.33, and then this is gonna begin at 0.25, ends at 2.25, and then this is gonna be 0.2, and then end at 2.2. So what's the pattern here? Well, the pattern is that the left-hand side, the left-hand limit, this 1 over n, as n gets larger, this guy is going to get smaller and smaller. In fact, the limit as n goes to infinity of this is equal to 0. So the left-hand boundary is getting closer and closer to 0. What about the right-hand boundary? Well, we have 2 plus, this is going to be 2 plus 1 over n. And as we've seen, this guy here, this goes to 0 when n gets large. So the right-hand boundary is going to get closer and closer and closer to 2, right? So if I draw this on the number line, this is going to be 0, that's going to be 1, 2. All of them, it begins here, right? 1/3 and then 7/3, and then it keeps shifting over to the left. So it's gonna go like this, and then maybe, let me draw that in a different color, like this. But the important thing to notice is that this, the left-hand boundary is never going to go past 0, right? It's always going to be slightly bigger than 0. And similarly, the right-hand boundary is never going to go past 2, because this is 2 plus 1 over n. So it's always going to be slightly bigger than 2, right? So from this, what can we conclude? We can say that the union, so joining all of them, all the possibilities, all the values, here, the union of, let me put A belonging to A, and it's going to begin at 0, but excluded, right? Because this is going to get closer and closer to 0, but because it is the limit, it's never going to actually hit 0. So the union begins at 0 excluded, and then let's see where it goes to. It goes all the way out to 7/3. That's the biggest value that it can have, right? Because we can see that it begins at a 3, which is 7/3, and then it gets closer and closer to 2. So that's the biggest value. And then the intersection of A belonging to A. So what the values that they all have in common, right? We can see here that the left-hand boundary is basically going to begin at 1/3. And the reason that it's going to begin at 1/3 is because that's the biggest one, right? The left-hand boundary begins at 1/3 and then moves closer and closer to the left. So all the ones that go after it do have the value 1/3 included. It just moves closer and closer to 0. So it's going to begin at 1/3 included, right? And then it's going to end at 2 included, because on the right-hand boundary, these are going to get closer and closer to 2, but they're never going to actually hit 2. So all the sets are going to have this interval here in common. And that is it for item K. Now let's do item L, which is, it's kind of a similar idea here. And maybe we're just going to write down a couple of these sets just to give you guys some examples. So let's see. It begins at n and then goes all the way out to n plus 1, where n is in the integers, right? So one example here would be, let's do maybe c of -2, c of -1, c of 3, and then c of 5, and see what happens. So c of -2 is going to begin at -2, right? And then end at -1 excluded. And then c of -1 begins at -1 included, and then ends at 0 excluded. Maybe I'm gonna do c of 0 here as well. It begins with 0 included and ends at +1 excluded. And then c3, it begins at 3 included, ends at 4 excluded, and so on and so forth. So what we can see here is that basically it's going to take every single value in the real numbers, right? Because you can see that you can go from -2 to 1 excluded, but then 1 is included here. And then to 0, which is excluded, but 0 is included, so there's a continuum here, and it takes every possible value. So what we're going to say here in the integers, right? So what we're going to say here is that the union of our c belonging to c, since it can take every possible value, it's going to be the real numbers, right? And then what about the intersection? Well, they have nothing in common, right? So if you look at this, this has nothing in common with that. So the intersection for c belonging to c, that's going to be just the empty set. And that's it for L. So let's do M. M is similar. The only difference is that the left-hand boundary is excluded, right? So what we're going to keep this. So for L, let's see. Actually, for M, we're here. So it's the same idea. The only difference is that the left-hand boundary is excluded. And let me put in a couple of examples here as well. C2. So the left-hand boundary is going to be excluded. So C1 is going to go from 1 to 2, and then C2 is going to go from 2 to 3, and so on and so forth. So we can see that all the values between the integers are included in this, right? And let me put the union. The union of, this is A, right? A belonging to A for M. And maybe I should put this up here, the problem that we're working on. So this union here, we're going to take every single value, right? So between 1 and 2, you take all those values, between -2 to -1. However, we can see that the integers aren't included because -1, it's excluded here and excluded there. 0, it's excluded here and excluded there. So you're going to take on every real number except the integers, because now on the left-hand boundary, that is excluded, not included. So we're going to say that the union is going to be all real numbers minus the set of the integers, right? And then similarly, the intersection of A belonging to A, this intersection is going to be empty because, for example, this guy here has nothing in common with this interval here. So that's it for item M. And now let's do item N. Let's put this together here. So for item N, we are going to have, for each n belonging to the integers, let Dn be the set defined by minus n to 1 over n, where it's indexed by the integers, right? So we're going to go D1, D2, D3, D4, and so on. Sorry, it's indexed by the natural numbers. So let's put a couple of values here. So D1 is going to begin at -1 to 1 over 1. D2 is going to begin at -2 and then go 1 over 2. D3 is going to begin at -3 and then go 1 over 3, and so on and so forth. So what do we notice here? Well, we notice that the left-hand boundary is expanding, right? Because the limit of the left-hand boundary, that's just infinity. But the right-hand boundary, it's getting closer and closer to 0. However, it's never going to be 0, right? Because if I take the limit as n approaches infinity of 1 over n, this limit is 0, but it's never actually going to hit the value 0. So from this, let's put the union. So the union of D belonging to D, that's going to be, well, the left-hand boundary is going to go to infinity, so it's going to take every single value up to infinity, and then the highest value that it can go on the right is just 1, because we can see that the right boundary gets smaller and smaller, so 1 excluded, right? And then what about the intersection of D belonging to D? What do all of these have in common? Well, on the left-hand boundary, we can see that they all have -1 excluded in common, right? Because it goes -1, -2, -3. So -1 excluded is in every single set. So that's on the left-hand boundary. And then on the right-hand boundary, what are they all going to have in common? Well, this is going to get closer and closer to 0, right? So we're going to say it includes 0. Because, let me maybe illustrate this on a number line. So that's going to be 0, that's -1, 1, -2. So the left-hand boundary gets bigger and bigger and bigger, and the right-hand boundary gets smaller and smaller and smaller, but the right-hand boundary is never actually going to include 0, right? So it's never going to go past 0. This means that 0 is going to be inside every possible interval. So it includes 0, and that is it for item N. Okay, so for item O, we're saying that A is the family of N, where N is a natural number and P is prime. And so let me just highlight this here. So this set here, if I do let's see, Pn, right? So the first prime number is going to be 2. So 2n is going to be the set of all the natural numbers multiplied by that prime. So we're going to have 1 times 2, which is 2, 2 times 2, which is 4, 3 times 2, 6, 8, and so on, right? And then the next prime number is going to be 3. The next set is going to be 3n, and that's just going to be 3, 6, 9, 12, and so on. And then we're going to have 5n, and then 7n. So let me just expand these. So that's going to be 5, 10, 15, and this is going to be 7, 14, 21, and so on and so forth. And when we put all of these sets together, that's going to give us our family, right? So let's look at the union. So the union of P belonging to this family. Oh wait, no, the family is A. So I'm going to say for each P belonging to A. And this union here, well, because we're seeing what are all the values that it could take. And because we're looking at the multiples of prime numbers, and if we take all the prime numbers, we can pretty much get every possible number out there, right? If we multiply it by the naturals. However, the one number that's not going to be there is the number 1, because 1 is always going to be multiplied by a prime number, right? So we can see here that the first entry is always going to be missing 1. So we can see that the union, all the possible values it could take, are all the natural numbers, right? Minus the set containing 1. And then what about the intersection? Well, since these are prime numbers, they can't have numbers in common, right? I mean, one number that's going to be in all of them, because by definition we're looking at multiples of primes. So if you, for example, take all of these and then keep expanding them, you would not be able to find one number that is common to all of these. So that's just going to be empty. And that's it for item O. And now let's do item P. So for item P, this is a little bit more challenging because we have a Cartesian product, but we can do it. So each t is going to be indexed by the natural number. So we're going to have t1, t2, t3, t4, and so on. And now let's look at how these sets look like. So this is a Cartesian product. So I'm going to put this out on the plane. And x is going to be between 0 to 1, right? So we're going to have, maybe here, let me put this 1, and that's going to be 1. So x is going to take in every single value between 0 to 1. But what about y? Well, for t1, because this is indexed by the natural number, so we're going to have t1, t2, t3, and so on. So for t1, we're going to have all the x's that are between 1 and 0. But then the y is going to be less than or equal to x to the power of 1 and 0. And then for t2, x is going to be between 1 and 0. And then y is going to be less than or equal to x squared, 0. And then for t3, x is going to be the same. And then y is going to be less than or equal to x cubed and 0, and so on and so forth, right? So for t1, x is going to take all these values, but y is going to be less than x to the power of 1. So if we plug in y is equal to x, that's going to be this line right here. And then it's going to take on every value less than that, right? So this is going to be for t1. Maybe I'm going to color that in. This is t1, right? So what would t2 be? Well, t2, and maybe I'll put that in a different color, we're still going to have x between 0 to 1, but now y is going to be less than x squared. So x squared is going to go like this. So t2 is going to be all this stuff here, right? And then t3, let me put a different color. So t3, similarly, x, oops, that should have been a 0 here. X is between 0 to 1, but now y is going to be less than x cubed. So it's going to be even flatter like this. So it's going to be like this. And we can already see the pattern, right? That as n gets larger and larger and larger, the curve is going to get flatter and flatter and flatter. So it's going to get flatter and flatter and flatter. So in the limit, when n is super large, we are basically just going to have a line that goes from here to here, and then a line that goes from here to here. That is what happens in the limit, right? So once we've understood this behavior, now let's just do the intersection and the union. So the intersection, the first let's do the union. So the union of t belonging to t, that's going to be every single value that it can take. And we can see here that the biggest shape that it could have, the biggest area, is pretty much going to be all the stuff that is in this triangle here, right? So this is the union. It can take all the values that are contained in that triangle. So the union, we're going to have, the way that we can describe this, let me put that, is the, maybe we're going to say the triangle beneath the y is equal to x line from x 1 to 0. So I'm just describing it in words, but now we're going to put it in a set. So the union is going to be all the points x, y, such that x is less than 1 greater than 0, right? And y is going to be, and y is less than or equal to x. So that's the union. And now let's do the intersection. So the intersection of t belonging to t, first I'm going to describe it into words, and then I'm going to put it in set notation. So the intersection, we're going to have, it's going to basically be this L-shaped. It's going to be the line, maybe I should put the horizontal line from 0 to 1, and the vertical line from 0 to 1, right? So this is kind of informally describing it. So once we've kind of gotten this notion, and let me just maybe highlight it again, that the intersection is going to be just this line here and this line. That's what they're all going to have in common. Now let's put it in set builder notation. So we're going to say here, that's going to be all points x, y, such that, first, we're going to break this down to two chunks, right? We're going to say such that x is going to be less than, actually not equal to, it's going to be less than 1. So x less than 1, greater than or equal to 0, because that takes account the horizontal line. And then union the set x, y, such that x is equal to 1 and y varies from 0 to 1. So y less than or equal to 1, greater than or equal to 0. Because when we break this down into two chunks, now we can say that those are two distinct things, right? The horizontal line and the vertical line. So that is it for problem P.